Today we are going to discuss about the Norton's theorem, verification of Norton's theorem. So here the below one shows the circuit diagram for verification of Norton's theorem. Here I want to determine the current to this 1 kilo ohm resistance. Okay. Now this is the direct inspection method. So that is the reason I am connecting ammeter directly to the 1 kilo ohm resistance. Okay. Now we need to verify this result with the Norton's procedure. Now this is the Norton's procedure. Here this is the Norton's equivalent circuit. Okay. Now here we need to determine this Norton's resistance as well as Norton's current. Now to determine this Norton's current as well as Norton's resistance, we require these two circuits. Now this circuit shows the Norton's current, this circuit shows the Norton's resistance, this circuit shows the equivalent circuit of your Norton's theorem. Okay, practically. Now first I am going to give this connection. So here this current must be is equal, that means the direct inspection current must be is equal to the Norton's equivalent circuit current. These two must be equal. Okay. Now I am going to connect this circuit. Now here for that I am taking 1.8 kilo ohm resistance. I am going to place this 1.8 kilo ohm resistance anywhere on the breadboard initially. Take another 1.8 kilo ohm resistance. Now connect this 1.8 to the second end of this R1. Now this is your R1 second name. Connect here. Okay. And the second end you can connect anywhere. Okay. Thereafter take another 1.8 kilo ohm resistance. Okay. Now this is called R3. Okay. R3 first end is connected to the R1 second end and R2 first end. Now where is this place on the breadboard? See here. This is the place. Okay. Now here we need to connect the R3 first end. Okay. Thereafter you can connect this second end anywhere on the breadboard. Okay. Now here this R1, R2, R3. These three are placed here. R1, R2 and R3. Okay. Thereafter connect this ammeter. Now see, ammeter positive is connected to R2. Now see, this is my ammeter. Ammeter positive is connected to the R2 second end. Okay. Thereafter ammeter negative anywhere on the breadboard. Connect this anywhere on the breadboard. Thereafter see here 1 kilo ohm resistance. First end is connected to the ammeter negative. Ammeter negative. Now see, this is my 1 kilo ohm resistance. Sorry, this is not. Here this is my 1 kilo ohm resistance. Okay. Now I am going to connect this 1 kilo ohm resistance to the ammeter negative. Okay. Thereafter the second end of this 1 kilo ohm resistance is connected to the R3 second end. Where is R3 in the breadboard? This is our R3 second end. Now place this end here vertically. Now here I am placing that. Okay, now resistance is placed, 1 kilo ohm resistance. Thereafter, see, RPS positive is connected to the R1 first end. Now this is your R1 first end. Now I am taking this RPS positive. So see here, RPS positive is connected to the R1 first end. Okay. Thereafter negative, RPS negative. See here, RPS negative is connected to the R3 second end. Where is R3 second end? Here. Here this connection is completed. Okay. Now this circuit connection is completed. Now we need to apply this voltage, either 15, 10, 25, your wish. You can apply any voltage. Okay. For demo purpose, I am applying the voltage as 15 volts. Okay. Now I am going to switch on the supply. Now apply the supply voltage as 15 volts. Now voltage is 15 volts. Now note on this current value here. It is 1.57. Now note on here. It is 1.57. Now this direct current, this direct inspection current is equal to the Norton's equivalent circuit current. This IL dash must be is equal to this IL. Then only the Norton's theorem is verified. Okay, this is direct inspection method is completed. Thereafter we are looking after this Norton's procedure. Now I am going to give the connection for this circuit. Now here, for that I am going to place all these resistors same place. There is no change in these resistor places. These all the resistors are in the same place. Now if you observe the circuit, in this circuit, see here, 1.8, this R2 second end is connected to the ammeter positive. Now see here we have the ammeter positive. See here, ammeter positive. See here, ammeter positive is connected to the R2 second end. Now see here, this is my R2 second end, connect here. Okay, thereafter see here, ammeter negative. In the circuit, ammeter negative is connected to the R3 second end. Now where is your R3 second end in the circuit? In the breadboard, this is your R3 second end. Now connect this ammeter negative to the R3 second end vertically. Okay, ammeter connection is complete. Thereafter we need to connect this RPS. Now where is RPS first end? That means positive is connected to the R1 first end. Now here this is your R1 first end. Now take RPS positive. This is my RPS positive. This is connected to the R1 first end. Okay. Thereafter, if you observe this RPS negative, it is connected to the R3 second end. Now here this is your R3 second end. Now connect this ammeter negative to this R3 second end. Here we need to connect vertically on the same place. Okay. Now this connection is completed. Now again apply the 15 volts. Why? Because previously we applied the supply voltage as 15 volts. Now I am going to switch on the supply and apply the voltage as 15 volts. Now 15 volts. Now we got the current as 2.2. Now this current as 2.20. This is called Norton's current. This is called Norton's current. Okay. Thereafter we need to measure this Norton's resistance by using multimeter. Okay. For that, again I am removing all these connections. Here this connection is similar to your Thevenin's equivalent resistance circuit. Now see here if you observe the circuit, these two are connected in parallel. Now see the parallel connection of these two. Now see here, this is the parallel connection. Place first ends are in the same place, second ends are in the same place. Now this is the parallel connection. Now see here, this second end of this one is connected to the R2 first end. Now take this again 1.8 and connect here, and second end some other place. Okay. Now see here, at this place R1 second end, R2 first end, R3 first end. That means three terminals are connected. Now see here, 1, 2, 3. 3 are connected at the same place. Now we need to measure the resistance between these two terminals by using this multimeter. Okay, by using multimeter I am going to measure. Okay. Now initially we need to place this arrow mark in the resistance position. Okay. Thereafter measure the resistance between these two terminals. Okay. Now if you observe the value, we got the value as 2.40. Okay, 2.39 resistance value. 2.39. Now note on the value here, 2.39. Okay, that means 2.7 approximately is equal to 2.7. Now I am going to connect that 2.7. Here we need to take the Norton's resistance as 2.7, and here we need to apply the voltage to get the Norton's current. To get this Norton's current, we need to apply the voltage. Okay, how much we need to get? This current we need to get. This current, this 2.2 current we need to get here. Okay, now to get this 2.2 we need to apply the supply voltage by using RPS. Okay, now for that I am giving the connection. See here. Here this is a 2.7 kilo ohm resistance and place anywhere on the breadboard. Okay, now this one is placed. Now I am going to take 2 ammeters for this. Okay. Now here first ammeter, here first ammeter is connected to the Rn. This is called Rn first end. Okay. Now next we can place this, otherwise connect this negative to here, connect this ammeter negative to here and positive anywhere on the breadboard. Here this ammeter positive anywhere on the breadboard and negative connect at resistance Rn. Okay. Now if you observe here, RPS positive is connected to the ammeter positive. Now here this is my RPS positive. RPS positive is connected to the this ammeter positive. Okay. Next see here, RPS negative is connected to the Rn second end. Now this is my Rn second end. Okay. Now negative connected to the Rn second end. Okay. Thereafter Rn first end we need to connect another ammeter positive. Now say this is my second ammeter positive. Okay. Connected to this place. Now say at this place 3 elements are there. Okay. First ammeter, second ammeter and resistance here. First ammeter, second ammeter and this resistance placed in the same position, same node. Okay. Thereafter this ammeter negative connect anywhere on the breadboard. This ammeter, that means second ammeter negative connect anywhere on the breadboard. Okay. Now from here, if you observe here, second ammeter negative is connected to the 1 kilo ohm resistance. Now take 1 kilo ohm resistance. Okay. And connect this 1 kilo ohm resistance here. Okay. Now second end of this resistance is connected to the Rn second end. Now where is your Rn second end? Here this is your Rn second end. Now connect this second end to here. Now the circuit is closed. Okay. This is the circuit diagram for circuit connection for your Norton's equivalent circuit. Okay. Now apply the voltage by switching on the supply. So all are switched on. Wait a minute, I am connecting another multimeter. I think this is not working. Another ammeter. This is not working, I think so. 1 second. Okay. Now here I am going to apply the voltage. Okay. Here we need to get 2.20. Why? Because we need to apply the Norton's current. How much we got the Norton's current? Here it is 2.20. We got the Norton's current as 2.20. That is what we need to apply in this. This is your first ammeter. This is your second ammeter. In the first ammeter we need to apply the 2.2. Okay. Now I am applying this 2.2. Okay, in first ammeter we need to apply 2.2, this one 2.2. So here we need to apply the current as 2.2. Why? Because we need to apply the Norton's current. Norton's current as 2.2. This meter is connected here. 2.2 is applied. Then note down this value. It is 1.54. Now note down this value here, 1.54. Here this value is 1.54. Now verify this result, whether we got same value in the previous case or not. That is direct inspection method. Now here in direct inspection method we got 1.57. In Norton's procedure we got it as 1.54. That means hence the Norton's theorem is verified.